Aliasing is one of the most fundamental concepts across fields from digital audio and computer graphics to radar and medical imaging. It describes how high-frequency information, when sampled too sparsely, can masquerade as lower frequencies. In this video, we'll see exactly why sampling below twice your highest frequency causes foldback artifacts, and how to predict the aliased result. To understand why this happens, let's briefly recap sampling and the Fourier transform. Sampling is often thought of as taking a time series signal and measuring its amplitude at discrete time intervals. This is one type of sampling, but definitely not the only type. You'll also see this concept of sampling applied to other areas, like the spatial sampling that I used to discuss phased arrays in a previous video. For now, we'll focus on time domain sampling, but we'll come back to the application of spatial sampling later. Sampling a time domain signal means measuring its amplitude at discrete time intervals. In this case, the distance between each of these samples is measured in seconds as the sampling period. But if you're sampling in space, this might be measured in meters instead. The distance between these samples is extremely important because it'll determine which signals we can accurately detect. Let's see why. Say this is a 3 Hz sine wave, meaning every second it'll oscillate up and down 3 times. If this is a second, then these 10 samples are spaced at a sampling period of 100 milliseconds apart. You could also say that we're sampling 10 times per second, or in other words, we have a sampling rate of 10 Hz. If we connect the dots between these 10 samples and fade out the time series input, we see that this does an okay job at representing the signal. It's not quite as smooth, but you can still see that it roughly oscillates 3 times per second. Increasing the sampling frequency would decrease the time between samples and make this look even smoother. But by the same token, as we decrease the sampling frequency, we start to get a coarser looking signal and lose information. Without knowing anything about the original continuous time signal, if we were to try and reconstruct this sine wave after lowering the sampling frequency, we can see that the samples go down, then up, making one oscillation, then go down and up, making a second oscillation. This really just looks like a 2 Hz sine wave now, instead of the actual 3 Hz it should be, right? This means we're completely misrepresenting the input signal because we're not sampling quick enough. Now, you may be wondering what frequency you need to sample at to avoid this unfortunate aliasing effect. Well, there's a very famous rule called the Shannon-Nyquist theorem, which states that if you sample at a frequency which is at least double the maximum frequency of your input signal, you can accurately recreate the signal. To adhere to this rule, let's try making our sampling frequency a little over double the input signal's frequency. So, for an input signal frequency of 3 Hz, let's try 7 Hz. What we see is that we now get 1, 2, 3 oscillations in the span of that 1 second, which is a 3 Hz signal. So we've successfully reconstructed the signal. What you've just seen is a huge issue in sampled systems of all kinds, and is one of the main factors you'll have to consider when designing such a system. One of the big places this is relevant is in phased arrays, which are basically samples separated by space instead of samples separated by time like we just saw. Aliasing in a phased array occurs when the array's individual antenna elements are spaced further than half the signal's wavelength apart from each other. This aliasing causes something called grading lobes, which are a super interesting topic that I'll cover in more depth soon. But to understand grading lobes and aliasing in general, it'll be useful to look at how this concept that we just saw in the time domain looks in the frequency domain. Time and frequency are inversely related, meaning you need a wide range of frequencies to represent a sharp pulse in time, and vice versa. So this means the inverse of the sampling period in time is the sampling frequency. This sampling frequency determines what frequencies we can accurately see when we convert the input signal to a frequency spectrum. But what's actually happening in this conversion? Well, when we sample a signal, we're basically multiplying it by an ideal train of Dirac deltas, or infinitely narrow spikes spaced every sampling period, like we just saw. This right here is called a Dirac comb because it just looks like a comb and it's made of Dirac deltas. It's kind of like poking the signal with a pin at regular intervals. Now, here's the really cool part. Converting this impulse train to its frequency domain representation gives another impulse train, still regularly spaced, but now across frequency instead of time. I won't get into why this is, but it's kind of interesting, so I included it in the Python notebook in the description and on the website. By the way, if any of this is helpful to you, consider subscribing. It really helps out a lot. So since we're multiplying the input signal by these deltas in the time domain, in the frequency domain, that means we will convolve the two. Again, I won't get into the inner workings of the convolution, but this will simply give us copies of the input signal's frequency spectrum centered around each of these deltas. And guess what the difference between each of these copies is? It's the sampling frequency. Each of these copies lives in their own zone, separated by half the sampling frequency, which we call Nyquist zones. And here's where the aliasing comes in. Before I move forward though, for simplicity, I'm going to briefly change the input signal to one that will give us a rectangular frequency spectrum. This is completely different than the sine wave input we've been using, but it'll make it easier to see the concept of aliasing in the frequency domain. And I'll come back to the sine wave in a second. Right now, what we see is a bunch of copies of a frequency spectrum that has a bandwidth that is less than the sampling frequency. And actually, we only count the positive frequency components, so the bandwidth is less than half the sampling frequency. So it complies with the Nyquist-Shannon criterion we saw earlier. But what if we started to increase this bandwidth to take up more and more of this sampling frequency? What you'll notice is that as we cross a bandwidth of half of the sampling frequency, these copies start to overlap with one another. This distortion is the aliasing, and as we just saw, it occurs when we try to sample a signal at a sampling frequency less than double the signal's max frequency. This is an issue, but maybe that issue will be more clear if we go back to the sine wave input we were using earlier. Again, here's the sine wave at 3 Hz we were using, and say this is at a sample rate of 10 Hz, or 10 samples per second. What we see if we plot the signal's frequency spectrum is a spike at plus 3 Hz and minus 3 Hz, since it's only a single frequency in the signal. The negative portion here is really important, and it affects us a lot, as we'll see in a second, but I won't really go into how I got here other than just saying it's due to the input signal only having a real, non-imaginary component. But again, I'll include that explanation in the notebook. Now, notice that this is only showing the first copy, otherwise known as the first Nyquist zone, or negative half the sampling rate to half the sampling rate. In our case, since we're sampling at 10 Hz, the spectrum will be from negative 5 Hz to 5 Hz. We'll still get all those copies though if we extend beyond the first Nyquist zone to the second zone, third zone, and so forth. This is all looking fine right now, since this sine wave falls within a single Nyquist zone. But if we start increasing its frequency, it moves closer and closer to the zone edge and eventually crosses into the other zone. Okay, a few super interesting things just happened here when the signal's frequency crossed the threshold of half the sampling rate. Now, the first Nyquist zone is the only zone we'll actually be able to see when sampling in real life. These other zones only exist in the math world, so let's zoom into the first Nyquist zone and slow down to see what's happening. As the signal's frequency crosses half the sampling frequency, it looks like it just starts moving in the opposite direction. But if we expand to show the second Nyquist zone, we see that it's actually just the negative component of the second Nyquist zone passing into the first Nyquist zone. But to us, with our limited one Nyquist zone viewing area, it just looks like the sine wave's peak is reversing course. You may have also noticed that for a second, the peak dropped to 0, but I'll get to that in a minute. Since it looks to us like the signal is traveling in the negative direction as we increase frequency, we can say that while the actual frequency is in the second Nyquist zone, the frequency we will see is the sampling frequency minus the actual signal's frequency. But that only applies if our real signal's frequency lands in the second Nyquist zone. Let's keep increasing it until it hits the third zone. Now in the region we care about, from 0 to half the sampling frequency, the peak from Nyquist zone 2 has left, and the peak from the second Nyquist zone on the left enters. It's kind of confusing that these are both labeled the second Nyquist zone, right? So as you can see, increasing the signal's frequency now increases the actual frequency that we see within that first Nyquist zone. As you keep increasing frequency, the signal peak will alternate between passing through even and odd Nyquist zones, causing it to go up and down within the frequency band that we're looking at. So within the first Nyquist zone, the part that we're looking at, from 0 to half the sampling frequency, there's literally an infinite number of possible frequencies that could actually be causing that peak. For example, if we see a peak at 3 Hz, it really could be a real 3 Hz signal. But it could also be a 7 Hz signal in the second Nyquist zone, a 13 Hz signal in the third Nyquist zone, or a 17 Hz signal in the fourth Nyquist zone. That's because these frequencies all alias down to 3 Hz when sampling at 10 Hz. And you could keep going, alternating addition and subtraction from the multiple of the sampling frequency. Knowing this, it becomes so much more important to choose a sampling frequency that is sufficiently high so that any frequency we care to look at falls within the first Nyquist zone. Otherwise, there's no telling where the peak in our band could be coming from. Okay, but I also mentioned that strange effect where the peak briefly drops to 0 at the Nyquist zone boundary, or half the sampling frequency. And this is confusing in part because I'm not giving you all the information about this signal's frequency spectrum. It's pretty common once you take your signal and apply the Fourier transform to get its frequency spectrum to take the absolute value of it. This just makes it simpler to see the full contribution of all the signal's frequency components. But let's say I remove this absolute value. What we now see is that the positive frequency and the negative frequency have a 180-degree offset from one another. So, as the positive peak in the first Nyquist zone collides with the negative peak of the second Nyquist zone, they cancel each other out while they're fully overlapping. If you were looking closely, you may have actually seen this in the first demonstration I did earlier in the time domain. When I sampled slightly under the Nyquist criterion, you see that all the samples briefly drop to 0, and then they invert in sign. It's pretty cool to see this happening in both domains simultaneously, right? This becomes an even bigger problem when we have multiple signals, so let's add one here at 2 Hz. If we keep increasing the first signal's frequency and it goes further into the second Nyquist zone, it'll eventually overlap our new signal's peak, causing it to cancel. Now, we have 2 frequency components, but it looks like there's nothing at all. And it gets even more complicated in real systems because the signal you're looking at will often span many frequencies. And there will always be noise everywhere, which complicates it even further. This is really just extra motivation to make sure you're sampling at a rate that satisfies the Nyquist-Shannon criterion. I actually wasn't planning on making an aliasing video, but I realized how essential this background knowledge is for pretty much all of my other videos, and especially some upcoming topics, so I hope you learned something and enjoyed. If you found this useful, check out my website in the description where you can find lots of Python notebooks with interactive examples and deeper explanations for all my videos. You'll also find some cool shirts and mugs and channel memberships where you can further support the channel and get access to additional resources and a private community, which has been really fun to interact with. Let me know in the comments if there are topics you'd like me to cover, and thank you so much for watching.